Okay, who's had a look at assignment 3? Bunch of you, that's good. I apologize about the even slightly more delayed release. What happened was that we had actually created your repos on time, but there was a glitch with adding you to your repo. If any of you pay attention, you'll notice that like the timestamp is different. So anyway, I think most of you got access yesterday Arvo sometime, I think was when the emails came through. So I appreciate your patience on that topic. I'm trying to figure out how best to kind of run through this. I might just try and run through it top to bottom. I'm turning the aircon on. Maybe I'm just hot because I'm running around. Sorry if everyone was cold. I can't turn it off now. So this assignment, I want you to think about it. The way I like to think about this assignment is think assignment 2, but because we taught a bunch more topics, we have to add more shit into it, right? That means smart pointers, that means templates, that means dynamic polymorphism. That means, I guess, like memory management's kind of part of smart pointers. So it's just like assignment 2, but more complicated and the stuff that comes along with it. The good thing is because you've done assignment 2, some of this stuff might be a little bit easier to digest. At its core, in assignment 2, you know that you had a namespace called FSV, which had a filtered string view in it, which was just a type that dealt with strings. In this assignment, we have a namespace called GDWG, or General Directed Weighted Graph, which has a graph class in it, and that graph has these 2 types in it. Now, these 2 types are the graph's node and edges. We know a graph has nodes, and we know a graph has edges. So if I was to think of a graph like this, how I could imagine it is, I was using this software earlier today. Okay, that's weird. Is like device. Sorry. That was meant to be a really elegant transition. Is that I have like a node here that has like, I'm a string in it, or a steering. And then I have another like node over here that's like, I am another steering. And they're connected by an edge, and it just so happens that that edge has a number on it. That's the number 6 there, right? So that's a graph. I mean, you normally draw graphs with circles, but rectangles can do, where you got nodes as strings and edges that connect nodes as integers. So that's the templated aspect of things with that graph. This graph, while we call it you'll see a lot of references in the spec to a general directed weighted graph. We did make, the main change we made this term was in relation to, we decided to make the edges polymorphically weighted or unweighted. That's the change in the assignment. So if you're going to see any weirdness, it's probably that part, because that's like a new part of the spec, whereas this spec has been used probably on like 3 or 4 terms in the past. So the edges themselves can be weighted or unweighted. So there is a theoretical scenario where you can have an edge between a graph that is not of a weighted type, but we can kind of come back to that. All nodes are unique. That is to say, no 2 nodes will have the same value and shall not compare equal using operator equals equals. So that's just kind of telling you that you can assume, there's some assumptions, that this graph will never contain 2 nodes that are indistinguishable from each other, right? Because if you have 2 nodes and they are true for operator equals equals, then poo-poo. It's not very good. It's hard to distinguish them. Yeah, there's just like a lot of text here. I don't need to dictate for you. This part's important. You need to make use of dynamic polymorphism to implement a base edge class from which unweighted edge and weighted edge classes will inherit. Okay, so instead of just having a generic edge, we have to have kind of like 2 different types there, and we can always unpack that again later. Lots of words in this spec. There's lots of definitions here too. So this spec was actually half rewritten by someone who tries to write a lot of technical documents. I really considered rewriting it to be in a similar format to assignment 2, and this isn't an excuse. My sick twister brain thinks like this. It thinks, the real world's kind of messy and every different project is new, so it'd be fun if this spec is a little bit different structure, because it just makes you think about stuff a little bit differently, right? And I know you might think he just didn't want to do the work. That's not true. You can believe me if you want, but I believe me very clearly. Definitions, very technical documenting there. So you can refer to those if you want to. I think some of these are kind of silly when they got added in back in 2019, like throws. I think you know what throws is. But still, if you're not sure, you can go look it up. But this is kind of where things get interesting and a bit more comfortable, because if you're like me, lots of abstract text scares you and you just kind of want to see some prototypes to write some code so you can get going with it. We can step through them pretty quick. We have a default constructor. We have a constructor that takes in an initializer list of type n. I don't believe we had an initializer list in assignment 2, right? Yeah, so a quick bit of Googling for that one. It's pretty actually easy to use. It kind of behaves a little bit, like it's a very straightforward thing. I don't want to kind of give it away. Again, some of the numbering here, this is also what I wanted to change, but I thought it would be interesting to leave it in. The way they've kind of written this is, I find it a little confusing because like this doesn't kind of clearly look like graph and then that, and then it looks like section 2 and then that and section 3 because the numbers all kind of stack up. But I'm pretty sure they wrote it that way, which kind of makes sense to me, as so that you can kind of more specifically reference things in the forum if you need to. Be like, hey, on point 5 of constructors, don't know. I don't write C++ technical documentation, so there's like, this was written by someone who actually contributes to the C++ standard, so that's why it's like that. I'm going to stop talking about the structure of the doc now. So every time you see a code box is basically another thing to implement, is how to think about it. So that's the first thing, a default constructor. That's a constructor that deals with initializer lists. This one, also of type n obviously, because it's nodes of type n. This one is a templated one that can take in an input iterator. The reason that this is templated is because there's different types of input iterators. That's something for you to think about. What we mean by that is like, I hope I don't have anything up in that. Yeah, okay, cool. So like, you know, if you create a vector of ints, let's imagine you have a graph for a second, a graph of ints and doubles. Easy. Let's say you're constructing that graph. What you might pass in is a vector or a dot begin and a dot end of a vector, right? Which contains all your nodes. Well, what type is that vector dot begin and dot end? It's of type standard vector int iterator. You could also, if you created a graph of standard strings and ints, you could also pass in standard vector of standard string iterator like that, you know? Like, so this, if you, let's say I had this was G2, you'd have G2.begin, G2.end. These two types here are of, these two values here are of this type. So what this constructor is saying is that you can pass in any valid input iterator. It could be a vector of ints input iterator, it could be a vector of doubles input iterator, it could be a forward list of ints, it could be a list of ints, you know what I mean? Anything that has a dot begin and dot end that could be treated like an input iterator is fine there. That's why it's templated too, because it could be a vector or a list or a forward list or any type. If we wrote this differently and we said we only want you to be able to construct graphs given a vector of nodes, we would have probably written it like this. We would have said standard vector n iterator. Does that make sense? But because standard vector n iterator, because all STL container iterators are of type input iterator, or not all, but like many of them are, we can instead do that. It's a funny little one there. Please just stop me. Also, to everyone on YouTube, I have to check your comments intermittently because the computer here isn't working today. Also, if anyone, does anyone want to volunteer to have the YouTube up in a tab and check it every few minutes? And yeah, my friend, thank you. Any questions so far? I'll give you a minute. Shouldn't rush you. We have our move operator, this looks like. Yep, takes in an R value reference. We know that it's a non-const thing with 2 ampersands. Then we have our move. Sorry, that's our move constructor. This is our move assignment. Makes sense. That's our copy constructor. That's our copy assignment. We should be familiar with those from the last assignment. They're our constructors. So at face value, the cool thing about a lot of that is that it feels, again, very similar to the last one, just with a bit more, just with like a bit more to do, you know? Not just copy constructors and stuff, yeah.
So, first one, turn up the volume a bit.
Oh no, what did I do? Turn up the volume a bit.
Yeah.
Damn it. The number.
I think that was like about 1, 2, super graph, and 3 was.
Yes, the numbers do only apply to the code block above it.
Yeah, right. And then, are there any restrictions on what types can be used for nodes and edge weights? Can an FSV be an edge weight?
That's a great question. I don't have the whole spec off the top of my head, but I think generally so. I think naturally, again, in your class, you're going to use certain operators, like less than or equals to or output operator. And naturally, if you use a type that doesn't have those defined, then it won't work, because the compiler will just crash. But if you do have them, I think it should be fine.
And a quick feedback is that moving 7 now.
The what?
Moving is good enough.
Oh, great. Thank you. Thank you. Thank you for taking on the responsibility. So there are constructors. The constructors should be fairly manageable. But now we get on to edges. So the thing is that this is the new stuff that we've been writing. So bear with me. This one's I'm a little like less comfortable with it. But you're going to create an edge class that is a parent class to what will be 2 subclasses, which will be weighted edge and unweighted edge. So the edge class is an abstract base class that declares pure virtual functions, which must be implemented by its derived class. That is simply stating what we said in week 7, right? So abstract base classes mean you can't instantiate it, but they can be inherited. They can have something inherited. And every function in there, well, not every, they should be pure virtual functions. Remember, a pure virtual function is like if I have a function, a pure virtual function says virtual out the front, and then it says equals 0. That's a pure virtual function. Note, we didn't specify the keywords for functions such as const, virtual override, or no except. This is intentional. You should use them where appropriate. Yeah, so we're giving you these things, and we want you to figure out what should be const or no except or virtual or anything else. That's kind of part of the challenge. Assignment 2e, a little bit. This is a function we have called print edge, which is, it's one of the returns a string. That's probably just going to call the underlying operator, I imagine. Returns a string representation of the edge. String representation of the edge. Oh, sorry, my bad. The format of the string representation is source to destination, then that if the edge is weighted.
I think there's an example on that.
Yeah. Sorry?
I think there's an example about like precisely what the output would look like.
Yeah. We do have it. We do have an output operator. Let me come back to the output ones because we do have a couple diagrams in here as well. But a lot of these is weighted. So like you can imagine this kind of pretty simply. If you have a weighted edge and an unweighted edge, they're both going to inherit the edge class, and one of them will implement is weighted by simply returning true, and one will implement is weighted by returning false. We also have getWeight, which will return the weight. It says it returns null_opt, which is one of those C++ abstractions like null pointer, if the edge is unweighted. And we have getNodes as well. GetNodes returns the source and destination nodes of the edge. Okay, so because every edge comes from a source and goes to a destination, and in that case it's always 2. That's why we return a pair, right? Because every edge has to start and finish somewhere, even if it's the same type. As a polymorphic base class, edge should also have a public virtual destructor. Weighted edge, unweighted edge, it must implement. Yeah, I think like a lot of that you can kind of read. I'm just trying to give you the gist of it. So that's the edge part. So you can kind of see there that in terms of the structure a little bit, because if you're trying to think about, and we actually have a compulsory internal implementation, which you'll see lower, but if you're trying to think about how you might store this, you think, okay, well, this actually makes sense now, because you think about what did we learn back in week 7? Well, if I have the graph, I was like, what's the graph class? The glass. If I have, say, my edges, well, you think, well, my edges are going to be standard vector. Like maybe I just have a vector of edge, and somewhere else I define class edge. And then somewhere I define class weighted edge, which inherits edge. And then somewhere else I have class unweighted edge, which inherits edge. And then, yeah, I think I have a vector of edges like that. Or, and again, well, this is kind of moot because we'll look at the representation. But, you know, if you need to store pointers to those edges for some reason, that's when we need to think about either storing like pointers to them or even better, standard unique pointers to edges as well, right? But again, you will have to do something ish like that in the assignment probably, but leave that alone for now. Yeah. The unweighted edge. The unweighted edge. No, not really.
It's not like it's seen as weight 1, but then there's like no other significance. So for instance, we can have like one unweighted edge between two nodes and then a weighted one.
Yes.
Of the same direction with weight 1, but like that doesn't have difference.
I believe so, yeah. Hey, look, I mean, I'm not going to sit here and say that's a genius idea. Like, it basically came to, we had an assignment 3. They rewrote an assignment 3. They rewrote assignment 2 and assignment 3 last year. The assignment 2 they rewrote is what you did. I thought it was a great assignment. The assignment 3 they rewrote, I wasn't that sold on. So I was like, I want to throw it in the bin. Let's go dig out the old one. But the problem was, one of the things the other assignment 3 that we've been tried to do was introduce dynamic polymorphism in the assignment. Sorry that I'm like keep talking at you now because you're like a proxy, but like they tried to introduce that and I was like, well, we can't go back to an old assignment and then cut out an important topic. So this is us kind of jamming it in awkwardly, you know? So like what I mean is I wouldn't spend a lot of time, people out there on the internet, trying to rationalize exactly, be like, you know, how does this weighted, unweighted edge thing make a lot of sense to me? Because it probably doesn't, because my instruction to tutors when we were brainstorming it was like, we need to think of an easy, lightweight way, because the less we change the spec, the less likely it is to be broken, which makes your lives easier, to like make this interesting and make you have to think about these concepts. So this was, I think, a great job they did. And that's why it also feels a bit weird, because it's like, okay, sure, unweighted edges, interesting. It's much easier than doing like polymorphic graphs or something. So if we have a look at some of these other functions, the graph now will have an insert node, which makes sense because you pass in a node. It has an insert edge. This one's a bit more funny. You pass in a source. You pass in 2 nodes, right? Because when you want to insert an edge, you need to give it 2 references to nodes that already exist, because you can't insert an edge without knowing where it connects between. And then we've got this thing here, standard optional. I don't think we've done much with standard optional in the course. Standard optional of an edge weight, which is by default null opt. So standard optional is a C++ type that basically you give it the template type T, and I'm pretty sure it can be, it's something like it can be either, I really should just read this. It's like it can be null, is it? The object is initialized value type null. I've forgotten what it is off the top of my head. Yeah, I mean, it basically can be like, it can be null optional. Like, you can wrap a type in optional if you want it to be that type or nothing. You kind of know this idea from pointers, right? Because you know with pointers, you can either point to something or you can be null. So you have like an empty case, so to speak. But when it comes to variables like a string, you don't really have like, I'm either a string or nothing. You only have, I am a string, maybe an empty string, but I'm always a string. There's no optionality to be nothing. So a standard optional is a C++ edition, C++ 17, which just allows you to be like, look, this weight is either an edge type or it's a null opt type, which is just like a, you know, an abstraction for nothing, a null optional type. It just gets you around, it gets you being able to do basically what JavaScript does with like null or Python does with none. It's the same thing. But it's because it's a typed language, we can't just like, we actually need to be able to say none. As an example, with JavaScript or TypeScript, if I make a type in TypeScript that I want to be a string or nothing, I actually have to say type name or name equals string or null. I have to do that, and then if I create like const name of type name equals Hayden, something like that, or that could also be null. So in these strictly typed languages, you actually need to specify that it may be null, and that's what we're doing here, is allowing it to may be null. There's a little bit of complexity in adding that. You can kind of read that if you'd like to. Replace node's interesting. It basically, you get the old node and then you give it a new node and it kind of replaces it. Replaces the original data, old data stored at this particular node by replacement data, new data, like that. We have another one here which is like merge replace node, which is similar. The node equivalent of old data to graph are replaced with instances of new data. After completing, every incoming and outgoing edge of old data becomes an incoming edge of new data, except the duplicate edges shall be removed. So it's funny, I read this and I think I like know how to say it till I actually have to open my mouth. But this one is like replace node, except it's just got some extra functionality. In this case here, pay close attention to except the duplicate edges will be removed, because you don't have a requirement like that in this one as well. So just slight different functionality. We do also have this diagram. This is a really funny diagram, but I think when we pulled this spec together in 2019, we wrote it, and then one random student posted this on the forum and was like, "Is this what you mean?" And I was like, "That's a cool diagram. Can I put that in the spec?" And they were like, "Okay." So now it's in the spec. Some rando student that's probably well into their career at this point, just trying to explain how that will go about. So refer to that diagram, and if you don't get it, share a bigger diagram with more explanation, and I'll replace it if you get it right. Otherwise, we'll talk through it. Erase node removes it from the graph, and it also removes all incoming and outgoing edges. That makes sense. Erase edge. So erase edge. Basically, what you do with erase edge is that you give it the one node and the other node, and you give it the weight. Because remember, an edge, when you have node A and node B, there could be 3 edges between them. Does that make sense? So you have to say, okay, I want you to erase the edge between node A and B with that weight, which is either one of the directed weights or it's one of the unweighted edges, or the unweighted edge, I guess you would say. So that's how you remove an edge. Alternatively, and this is kind of foreshadowing another topic, erase edge. What erase edge will do is that you get given an iterator and it will erase that edge. Now, what this is foreshadowing is that you're going to have to make an iterator for your graph that allows you to iterate through the edges of your graph. So just so you can at least half understand that particular one. What this means is that at some point you will be able to go graph.begin, graph.end, put it in a for loop, and it will go through all the edges. And you can pick a particular point in that iterator and pass that in there. It's just the same as standard vector has its .erase function here, where you pass an iterator. It's the same thing. Vectors have iterators. You're going to have an iterator. It's just harder to imagine because the vector's like a nice little bunch of boxes, whereas a graph looks like a mess in your head. But again, we will get to that. Yeah. Yeah. So questions basically around what happens if I have a node that has no edges to it or from it. Is that part of the iteration through it, right? Yeah. I believe not, from what I remember reading and writing, but I think it'll be defined. I'll have a look in the spec when we get to the iterator part, but I'm pretty sure it's not in it. But again, I'll check, because it has to return edges at the end of the day. We also have erase edge where we pass in 2 iterators. That erases all the edges between I and S. I don't think is there an equivalent here? It's the same thing with vector 2. If you have a 10-part vector, you can pass in an iterator to the second element and an iterator to the 8th element, and it will just go and strip them all out pretty easily for you. We also have a clear, which erases the nodes from the graph. That's also, which erases the edges, right? Because if an edge needs nodes to live. If you erase a node, all the edges go as well. That's kind of implied, but not written there. We also have accesses. This is pretty easy. Graph.isNode, you give it a node to pass in. You're like, are you a node? It says yes or no. Is the graph empty? Are these 2 nodes connected in any way? Can you give me a list of all the nodes in the format of a vector? Can you give me a list of all the edges in the format of my edge class? Blah, blah, blah. Find. So you pass in 2 nodes, and then you pass in the weight. Like does it exist? You're trying to see if a particular edge exists between 2 nodes in the graph. You want to get a list of connections. So this one is like you pass in a node to the graph, and it shows you, it gives you all of the out nodes, I think, right? Sequence of nodes found from any immediate outgoing edge connected to source. A sequence of nodes found from any immediate outgoing edge. Yeah, outgoing edge. So it's like if you have a node with like, if you have 3 nodes, right? 1, 2, 3. And there's like an arrow going that way, and you say, get me the nodes of the middle one, you'll only return this one over here, because it's all like the outgoing edges. Because this node points to that one, but this node doesn't point to that one over there. That one points in like that. So again, the spec's quite clear on that. We have a begin and an end function. You can call graph.begin and graph.end, and you get an iterator. Oh, cool. But what is the iterator? The mystery that we still have to solve together. We also have a double equals. We have an output string. This defines how all the stuff's outputted for you. It's kind of, it's all written down there. We've got some code examples, and we have some actual examples of you testing it. That's what it should print out like. So the operator at less than we saw for the edge earlier is just doing this. So because this here is an edge, right? If you think about this graph, this is saying that there's a node 1 in the graph. This is a graph of ints. So all we're doing is printing out the value of that node, right? Because if you have a graph, in this case, it's a graph of ints and ints, it looks like. Graph of ints and ints, yeah. So this is an int node that has one edge from this int node to another int node 5 that's a weighted edge with value -1. Okay, but now I've got node 2, which points to both node 4 and node 1, but the edge to node 4 is an unweighted edge, so it has no value, and so forth. So that's kind of how you would print it out.
Okay, so
yes?
something about, on this topic. So Tim asked, when unweighted edges are treated as if they have weight of 1, so are they are weighted edges and unweighted edges to be sorted or ordered together? So in this case, right, we have so for the second node, for example, we have 2 to 4, which is unweighted, and 2 to 1, which is weighted and 1. But I think according to a bit about how we order things, something about so I think it says we order by nodes first, and then upon the same node we order by weights.
Sorry.
I think the keyword was ordered in the 6th.
Order. There we go. Then the rest of the weights edges are sorted in ascending order. This is a good example of something that's not clarified because it's new in the spec, right? So no one's asked the question. I will ask the team to make a small update, but my assumption here is that you can't compare an unweighted edge to a weighted edge, and because you can't compare it, I don't know. I imagine it's just going to be at the top. Because what happens if the edge is a string? It can't have a weight of 1 because the weight is a string. It's a little bit abstract. The whole idea of having edges is that aren't numbers is a very odd idea. But yeah, I imagine it's just going to be at the top, but I don't think anyone's asked that. So that's a good question. Get that clarified. Iterator. We get to work on iterators now. The cool thing about iterators is there's a lot of boilerplate, so you get to copy a lot of code. So this is the code. Like you're creating an iterator for a graph with generic types n and e, where your value type, right? Like you're iterating through structs of node to node with edge. This is just an edge type. You know what I mean? That's actually just the edge class, basically, in terms of properties. Void, pointer, difference, all that. Bidirectional. So this one's bidirectional. It's not random access. You kind of need to be able to move through things one by one. We have a few functions you need to implement. So the cool thing about the iterator is that, like the iterator class, you just take that and paste it into your code. But then you actually have to define the functions. That's where kind of the headache of it is. Because you've got your constructors and everything else here. So like here I've got like iterator constructor, value initializes all members. Sure. Now remember, this is the iterator itself. If you're so just on this iterator topic, I think this one always can confuse students. I think iterators are a bit of a weird concept in general. What I would say is the good thing is you should be able to do a lot of this stuff last. So I would really get settled in the assignment first, I think. But when you do this particular part of the assignment, I would go back and review that rope example from week 5, if you remember that one where we had the rope, string of strings or whatever. Because I find, at least for me, that's always where I start, wherever I'm kind of a bit confused about what iterators are doing, because that one helps me kind of connect it together. Because remember, the iterator is a class by itself that stores basic information about the graph in order to move through the graph. So, because again, we could go back to the rope example, but the iterator is typically friended with the graph in a way that it can see its internal representation. So your iterator knows the internal representation of the graph, and it can move through it however it wants to. And it's just keeping track of some basic stuff to figure it out. Yep. So we have our default constructor, constructs an iterator to a member element within the graph. I'm actually suddenly a little unsure what we mean by unspecified there. Let me come back to that one. Now, so imagine, let's say this is a graph for a second. This graph is made up of a series of nodes, which is 1, 7, 12, 19, 21, 31, 14, and 67, right? Okay, they're all the nodes in your graph. You could store them as a vector in your graph if you wanted to. Then we have edges, and the way that edges are stored generally is edges are stored as, if I'm just thinking in light terms, a list of 1 connects to 7 with weight 4 or edge 4, right? I'm just reading the image here. And then I also have another edge in my graph, which is, hey, 1 connects to 12 with weight 3. And I also have another edge in my graph where 1 connects to 21 via edge 12, like that. If that makes sense. That's how the edges are stored. They're a list of these little, not really tuples, like triples. Or is it a tuple if there's 3?
Yes.
Thank you. Yes, good. Yeah, I mean a pair's 2. Yeah, tuples more than some number of things. So it's basically a list of tuples. So when we say something like, hey, if I have an iterator, let's imagine and I'm trying not to write too much actual code for you because I want you to kind of, get pumped up, I guess. Because so next week we have a lecture on metaprogramming. I'm pretty sure it says on the timetable we have no lecture on the Wednesday, but more likely I'll just actually have a lecture up and just answer questions if people have it online. You just tune in. We'll talk about that later, but the point is if you have more questions, don't stress. But if I say have a graph called G, right, some graph, and I create a G.begin, well, what type's that going to be? If I say auto it equals G.begin. The type of that, if I had, say, a graph of, int of int, is going to be a type of graph int iterator. That's going to be the type of it. And what this is saying here is that, hey, if someone tries to dereference iterator, what are we going to do? Right? We have to overload the dereference here. So that's us trying to overload the dereference. This one here is what happens. We say, what happens if someone tries to, well, that one's pre-increment, I guess. What happens if someone tries to pre-increment the iterator? What do we do then? Yeah. Now, the iterator itself is not actually a crazy concept, because you kind of, like, the lecture on it was really explicit, and the code we have is explicit. You have to define these few functions. Where the headache comes from is the fact that the graph itself is not a linear object, right? Like, the rope was easy because it was just strings of strings, right? Like, it kind of has some notion of, it's like a book, right? Like, a book is in 2 dimensions. You've got a page, it goes up, it goes down, you've got words going that way, letters going that way, but you kind of know, you just read across it, read across it, read across it. It's not strictly obvious how you read that, you know, how you linearize it, how you serialize it. So we do have to define that down here. So in this particular graph, what we do is when you iterate through the edges of a graph, or basically iterating through the graph. Like, when I say iterate through the graph, you iterate via the edges. Is you start off with the lowest node in the graph. So you look at all the nodes and you say, what's the node with the lowest value? And then the first next node that you put there is you put the next node with the lowest value. And then if there's multiple edges between those 2 nodes, then you put the edge with the lowest value there too. You know, so basically the entire graph is just sorted in a way by operator less than, if you think about it. Because I can compare 2 nodes. Like, I can compare node A and node B, and one of them smaller than the other. I can compare edge A and edge B, and one of them smaller than each other. So if I just look at this graph, I'm like, okay, 1, what's the smallest node it connects to? 7. All right. Between those 2, what's the smallest edge connecting it? 4. Done. Okay. 1 also has 2 more nodes. 12's the smallest, so it should be 1, 12, 3, then 1, 21, 12. And then what's the, okay, so now I've done all the stuff with 1. I've done those 3. So then I think, okay, what's the next biggest node that I need to print out? Well, it's 7. 7's the second biggest node. Okay, well, what does 7 connect to? Just one thing, 21. So it must be node 7 connects to 21 with weight 13. So we've done that one. And then we think, what's the next biggest node? It's 12. What's the next biggest node? It's 14, and so on and so forth in that particular case. Yeah, that's the graph ordering, essentially. The reason we define that there is because you know, we're just trying to show you that when you increment it, that's how you figure out which next one to go to. That's a bit of a challenge. I mean, when I say challenge, I mean it's not like it's not like only geniuses can figure it out. It's more like, you know, it's a bit finicky. It's like word ladder. You have to sit down and be like, how in the hell do I do that? And then, you know, go and actually try and have a stab at it. We also have operator plus post increment. That can be defined in terms of this, which is really easy. We have pre-decrement, post-decrement. Again, the good thing is once you've defined a way to move through it in one direction, the other stuff gets pretty easy. So most of the effort's just in this first function. We also have iterator comparison. You need to be able to get 2 iterators and compare them. So if I get like a, you know, if I got my graph there, I should be able to say, you know, if I've got a g.begin and a g.end, I should be able to compare if iterator 1 equals iterator 2, like that. It's pretty easy. Yeah, that's actually pretty trivial to do because like each iterator just stores. Because like if you want to think about it, it's like what your iterator is probably going to store. I don't think we specify the iterator. Yeah, I mean we don't specify everything, but this is the internal representation of the graph. Let's read this first, then I'll talk about what's in the iterator. So your graph is required to own the resources that are passed into it through the insert functions. This means creating memory on the heap and doing a proper copy of the values from the caller. This is because resources in your graph should outlive the caller's resource that was passed in case it goes out of scope. Okay, so if that's feeling too abstract for you, what that means is that if we were to say have a function, we have a main function here, and then what I do is I'm going to go and create a graph. I'm not using the auto syntax, I'm just trying to do it quickly. I have a graph called G. Normally these things you would general directed weighted graph. You would normally namespace it, but we're not here. Then I have a function called blah. I'm going to pass my graph into that. And then imagine my function called blah, which takes in a graph like that. It is going to create a variable called 5, say int 5, int a equals 5. And then it's going to say g dot, what is it? What is the add node function? Is node insert node? It's insert node, right? Yeah. It's then going to say insert node 5. Should be fine. Yeah. So remember, we talk about this a little bit next week, but remember, 5 is an R value, but you can pass R values into functions that take const L values, which is this one. This wouldn't work if this wasn't const. Because if you pass a variable, if you pass an R value into a function that just takes in a const input, sorry, a reference input, it implies that you should be able to change that value. Actually, sorry, this one is an L value. I meant, okay. This currently passes in an R value because it's passing in an int literal. If I instead do that, I'm now passing in an L value. All of this has no relevance to insert node in the graph assignment strictly. I'm just giving you a bit of background while I'm there. But the thing is, if I pass in A into this, A as a name goes out of scope as soon as this function finishes. Right? So we call this function, A is defined in the function, then it goes out of scope at the end of the function, and then it's gone forever. So what we need is for it to outlive that. Because at this point, A is gone, but we want that 5 to exist as an item in the graph forever. So all we're saying is we're going to copy it in. So even though we pass everything into this graph as a reference, even though we pass A in as a reference, it's actually copying it under the hood. And it's going to be doing that by storing it on the heap. So basically, your insert node function is going to have the equivalent somewhere. If you had an insert node function, takes in a const, an n const reference or something called n. It's going to be like, well, my vector of nodes that I have inside my graph, let's pretend it's called nodes. It's going to be like dot push back standard make unique n. Does that make sense? Like you're basically going to like take in what's passed in, and then you're going to create a unique pointer to it. Now, naturally, you could also just like have a vector of actual nodes. Maybe that's okay. Let me keep reading. Don't want to say something silly. Yep, so your graph is required to own the resources. Don't worry about that make unique part yet. The point is it needs to be copied in at the very least. This is because resource in your graph should outlive it, blah, blah, blah. Yep, this is an example. It's probably really unnecessary of me to go and write that. We're just saying that you go and add hello to the graph. Hello goes out of scope. However, you can still access that in the graph because we copied it. Your graph is required to use smart pointers however you please to solve this problem. For each node, you're only allowed to have one underlying resource in the heap stored in your graph. Sorry, that's right. That's why I said it, because yeah, everything has to be stored in the heap. So you do need to make unique your nodes and edges because they have to be heap objects. For each edge, no matter its weight, no matter whether it's weighted or unweighted, you should avoid unnecessary additional memory wherever possible. So when we say like compulsory internal representation, we're not saying that like, here's the exact internal structure. But what we are saying is that when someone passes you in a new edge or node, you need to copy it, and you need to copy it into the heap, which means basically doing like a make unique or a make shared. Depending on your implementation, you're going to have to use a unique pointer or shared pointer. You can do things slightly different ways because what's tricky is you got to remember your edge class, if we go way back up the top here, your edge class kind of needs to contain the nodes, right? What I mean by this is like, let's imagine you were being really primitive with this graph. You would go and say, hey, I've got a standard vector n called nodes, and then I've got a standard vector of a standard tuple of n, e called edges. Right? That would kind of do it at a high level. Because I got a list of nodes, and then I've got another list over here that stores all this edge connects these two nodes together, and there's my list of edges, right? If you wanted to, that would be a fairly digestible way to do it. You could do it other ways, but The problem with this is you're going to have duplication. And you're not allowed to have duplication in this because every like time you add a new edge, you're going to be copying all the nodes, right? Because each node in this edge list is its own copy of it. So where things get really tricky here is that how you are probably going to want to store stuff, and I'm not saying this exact structure, is that you're going to say, well, I'm actually going to store a unique pointer of n, right? And in all of my edges, I'm going to have an internal structure where I actually store node pointers to a node, if that makes sense. So your vector list of your actual nodes is like your nodes, but then your edges, it's not storing all the big node data. It's just, what do we call it? Like, raw pointer, observer pointering the nodes. The other way that some people would try and do things is like shared pointer here, and then these become like weak pointers. Does that make sense? That's like the classic case of it. The good thing is I understand this assignment well, but it's been so long since I've had to write something for it. It's actually quite enjoyable to teach because I don't know how I'd approach it today either, having not kind of done it for a while. What I do know is that I feel like my gut tells me that, that whole thing about unique pointers being useful is probably true. And I would probably try and do it with unique pointers first, unless I feel like I hit a roadblock or it was just the wrong direction. But I'd at least start with unique pointers. Because if you think about the hierarchy of C++, it's like avoid all types of pointers if you can until you can't. Then you go to smart pointers, and avoid shared pointers, use unique pointers as much as you can until you can't. Then you go and use shared pointers at the end. Yep, it's kind of just what I said there. I mean, yeah, you wouldn't even need the vectors. You could just do the map thing if you want. And like people might do that map thing as well. The cool thing about this assignment is you do have a little bit of flexibility with how you do stuff. It's pretty open-ended. So like all of these things about raw pointers and smart pointers, it's never going to come through in the auto marking because the auto marking is really only going to be able to assess the interface, the API. All of this stuff about unique pointers, shared pointers, it's all going to be based on hand marking, if that makes sense. So there's no like, some people might be like, oh, are you going to give my nodes like 10 megabyte nodes and then pump it full of and see what happens? It's like, no, we don't have anything that advanced at all. All this stuff is pretty similar. Const correctness is pretty similar, do that job. Marking criteria is similar, git requirements, submission, dry run, dates, all of that, same as last time. So there's nothing like particularly new there. Just a lot, right? Like, it's worthy of a 30% assignment for the course. It's like a large assignment. But it's still big. And I think and this might be a mistake of mine in the end, but we released assignment 2 as early as we could. Then we made it due. We had a choice making it due in week 5 or week 7, if that makes sense. We made it due in week 7 because week 5 you all would have killed me, probably. Plus, like we hadn't taught operator overloading till week 4 anyway, so that would have been a bit tight. But yeah, one of the side effects of this is you just got to remember that it's due pretty soon. And I know here it says like, I'll probably go and update this and I'll post in the notice about it, but I'm not allowed to make things due on the weekend, right? Sorry?
So like any week 11 dues?
I'm not allowed to make things due in week 11. That's a Faculty of Engineering rule, or maybe a university rule now. And you can only do that if there's no exam for the course. And I'm not allowed to make it due on the weekend. That's a computer science and engineering policy. So it's due on Friday night. I'm also not allowed to make it due late Friday night, which is also a school policy. That was my doing. I feel proud of that one. I was like, I'm sick of assignments being due at midnight. Because I'm like, we're all like, all the university loves to be like, oh, we want to promote the health and happiness of our students, like put an oval in and stuff. And then they're like, we're going to make it due at midnight. You're not going to get any sleep because you're going to be up late. We used to have a course that used to make an assignment due at 8 a.m., which I thought was like the most tone deaf. Like, I mean, maybe they were intentionally like, messing with people a bit, but it was just like, that's not a smart idea, They're just not going to sleep, guys. Like, so I kind of started the trend of like, these like mid-evening deadlines and stuff. And then the school took the weekend. I didn't care about weekends as much. Like, I'm not that fussed at weekends. Not like annoyed at the rule or anything, but it's like, I mostly care about the 8 p.m. part. But the rules don't let me make it due later than that. However, what I can do, and I will do, and I thought about this week, is like, I can go and put a light late penalty on it, right? Because the reason we don't, again, remember the reason we don't have late penalties on other assignments is because we need to get into the marking and get them marked. Because if we put late penalties there, we have to delay marking a whole week, which means everything comes back later, and we have to delay auto marking, right? And students generally like to get stuff back quickly and start the next assignment. Like if assignment 2 had a late penalty, a lot of people wouldn't finish it till today. Do you know what I mean? Like 5 days or whatever. So what I'll probably do is I'll probably put a 3-day late penalty on assignment 3. 5 just starts to get into like, you just got to get it done at some point, and I don't like drawing out the pain. And we also do need to market it as well. But if I make a 3-day late penalty, then you'll all get till Monday night, which gives you that weekend as well. The late penalty will be a university endorsed 5% off your mark. It's a small amount, which is good for you, but it's still finite, if that makes sense. So what it means is that everyone here should try and get it done by the Friday. That's kind of like what it's there for. But if life's hard or you just don't get around to it, there's an extremely tiny penalty. A lot of penalties in CSE used to be like, I think it used to be like 20% a day, or like a common one was like 2% per hour kind of thing, things like that. So 5% per day is like just living the dream, realistically. And it is good that it's not off the cap, because some people always say, is it 5% off the max I can get, or is it an actual 5% penalty? It's a 5% penalty, because if we just said 5% off the max, put your hand up if you don't think you're going to get 95% of this assignment. It's like, someone, right? And therefore it creates this weird tone where it's like suddenly a bunch of people who feel like they're underachievers are going to get a lot more time than, you know what I mean? It gets a bit weird, which isn't bad, it's just a bit weird. So think of it like Friday the 2nd of August, but if you submit it Saturday, 5% penalty. If you submit it Sunday, 10% penalty. If you submit it Monday, it's going to be a 15% penalty. I will write that into a notice or the spec or something like that. Yeah, and we can talk about it next week. The lecture's not going to run for 2 hours on next week. Any questions?
Yeah, when will the mark for assignment 2 be released?
Oh, it's a good question. Soon. Let me show you real quick. I have to hide your Z numbers, if that makes sense. So, ooh. C++. How do I hide the Z number? Sorry, one sec. Hide field ZID. Perfect. Yeah, I think that's not very informative. All right. So this is it currently. This is sorted by marks. These are all the people getting 99, and then it goes down like this. I'm moving at a pretty constant pace here. Now, I don't want you to read too deeply into it yet. Well, I mean, maybe you should actually, because the fact that no one got 100 tells me that we have a bad test somewhere, if that makes sense. In a course this big, someone gets 100 for an assignment that's not too hard, right? So I just sort this out by Friday because, I don't think it's our fault. Like all of these people here, it's unlikely that all of these smart ones of you all did the exact same thing wrong because you've all failed the same test, So I'm like, okay, I'm looking at that at the moment. But yeah, that's the breakdown. I think what's important to remember is, and I'm just trying to think, I don't think any of this is like personally identifiable. It's not, I don't know. Okay. CMake output. Oh, stupid. It's all right. Yeah, it's like a lot of it's going to be, not every single case, but a bunch of it's going to be like people just had a compile error too. Because if you have one little bug in it or something, or there's some people that still had some obscure library problems and things like that. So I wouldn't read too much into it. You actually have to read the results. But again, we're still just double checking stuff, and we'll hand it out on Friday. Yeah.
Could it be like constant restart functions causing compile error?
Yeah, it could be. Yeah, exactly. Yeah, like we're just still kind of looking into it because it is still only the second round of time that this assignment's been run. Because word ladder's like the 7th time this course has used it, filtered string views the 2nd, and graphs the 4th in its like 15-year period. So it's quite new, so I'm quite dubious. But yeah, we're just figuring it out slowly. Naturally, there's still going to be people who get a mark back and maybe something's wrong, or maybe there's a rerun. That's all totally fine and normal, exactly like previous assignments. So, you know, just carry on there. Any other questions?
Yeah.
Yep.
So we're talking more about still unweighted edge. First one being, can we have like more than one unweighted edge between, I guess, two, like, so same source, same destination, multiple unweighted edge? No?
I don't think so. Again, it's a good question because it's part of the new.
Get a like blog post about like question about unweighted edges. So people have a question about like have things chucked into the same like topic. So it's easier to filter through and also better feedback for whoever wrote this.
I think like so the tutor who's managing the forum for this week and next week is the one who's managing the spec too. And I just as a rule, like I mean, this is just my view, but the one I try and avoid the mega posts because like I always think like if a student should ever read, if a student ever has value reading a mega post with all the clarifications, then the spec's just shittily maintained. So it's like if there's a question that might ever come up again, it's the responsibility on my team to make sure that they clarify the spec so that no one ever asks that again. So, and if they do ask it again, then I just need to help them do their job properly. But yeah, I mean, keep posting the stuff on the forum for sure. I'd say at the very least with any questions about the spec, you should at the very least make it public. There's no value in making a private post if it's about like a clarification because other people are going to search it. It avoids you having to write a big question. It avoids tutors having to answer the same person twice. But yeah, I'll get that. If they could post that on the forum too, because I'm just trying to remember, it's like multiple unweighted edges. I don't think that it should be possible though. Yeah.
And another one, so it's still about the fact that, so for at least for numeric weighted edge, well, so for edge weights that are numeric, in a case that they have default 1 for unweighted ones, so when we compare them, should we do like negative ones first and then 0 and then like unweighted?
Yeah, I still think that's probably back to that earlier question, which still needs to be clarified, which is like, how do you order an unweighted edge? But I still think the answer is going to be that they're just going to come before all the weighted edges, because again, if I have like all the edges are strings, like yeah, you can't just be like, oh, the unweighted edge has a default of empty or something. Like then how do you define that for every other possible type? It doesn't make sense. So there's probably going to have to be something around it comes before all the other types. Yeah.
So because of that, potentially like, shall we like perhaps like remove the sentence about it's also so like the fact that the unweighted ones has default weight of 1.
Yeah.
This also applies in this assignment, so it's somewhere in section 23 where we talk about unweighted edge. So yeah, I guess or like it was like further in the right beginning was also applied to this assignment. Yeah, so in the task, section 2, the task.
Yeah.
So it says that graph and blah blah blah. This applies to this assignment as well. So maybe that's not
Yeah, for sure. No, I mean, like, we'll just fix that up for sure. I mean, best thing is just ask questions, because like it's very simple normally. It's like you guys will ask a question, a tutor goes, because I have a couple of tutors who've helped with this rewrite, just because they get to stuff quicker, and they'll be like, oh, made a mistake, I'll get rid of that, and then they just push an update. And for something that they're not sure on, they just ask me, and then we make a decision together. So, but again, like the reason I'm not giving an answer here is because like I kind of sat down with them 6 weeks ago and was like, let's come up with how we're going to do it. And we came up with a plan, which we were all happy with. And they went and wrote this. So they've been writing it more than me. And like a big part of my job, just generally with, you know, being a decent manager of them is not to kind of heavy-handed just share my opinion. Because I might go back to them and be like, oh, I mean, we should probably get rid of that line. And they'll be like, no, it actually makes perfect sense why it's one. I can't see how that would be true. But I need to give them the professional space to make sure that they check it. But we'll make sure, yeah, that's going to get cleaned up, because like ordering of an unweighted edge plus default of 1. And sometimes what you see with stuff like this is that it can be really easy when you write specs. I've written a lot of assignments to write that, and then later on you just like kind of forget you ever wrote that as you actually flesh out all the details. But again, we'll get to the bottom of it. Any other questions or?
That's almost it. So like there are just like multiple variations about how unweighted edges are like should be.
Yeah, we'll clarify all that, everyone. I'm going to get onto multiple unweighted edges, which should be easy. All nodes unique. I just need to double check about the multiple, because like I'm pretty sure edges. I'd have to go through this with a fine-tooth comb. I just don't really like standing here reading and concentration. Because I'm pretty sure edges can't be like multiples. I remember when we wrote this a long time ago, because otherwise we would have shown it here, you know. But then again, we haven't shown multiple edges to the same node either, so maybe we just oh yeah, but back to someone's earlier question. I think it was yours even. It's like, in this case here, if you have a node that's 67, it doesn't have any edges anywhere. It just doesn't get iterated through, you know. You can't iterate through any, the node has no output here. That's why we include it in the diagram, because it's like, yeah. So any node you can kind of ignore, which is again part of the art of playing around with that iterator, is, you know, being able to be like, you know, start with node 1 because it's the smallest, but then we're only going to check it if it has other nodes to go to. Any other questions? I think just to ground you all a little bit more, remember that you're going to have a namespace, general directed weighted graph, and inside that you'll have your class graph. I kind of wrote this a little bit before. But remember too, like I wrote this earlier, your edge is also in that namespace, but itself isn't contained within the graph. And you can tell that pretty easily because it's just written right there, you know. However, your iterator is part of the graph. Because if you think about it, it's like you have, you know, general directed weighted graph edge, that's a type. General directed weighted graph graph, that's a type. General directed weighted graph, you know, N, E, whatever, iterator. So you can really infer a lot about how to structure this stuff based on what's going on there. I would still encourage a lot of you to leave the iterator till the end. I actually don't think, like, I know I make out like, ooh, big scary assignment. I think there's more work in this, clearly. There's more stuff there. But when I say it's harder, I don't think the assignment 2 functions were super difficult anyway. So I think all of you are very capable to do this. And I think there'll be a few tricky things like the iterator, but if you just got stuck in tomorrow and started like constructing a graph and go straight for the easy stuff like insert node, where's the accesses, is node, empty, you know, get me all the nodes. I mean, you can kind of do all the stuff that does with nodes by themselves, and then you can be like, okay, now we're going to add edges between the nodes, and that's a whole chunk of work by itself. That's kind of the mantle of the assignment. And then there's kind of a bit at the end to do with the iterator. But what might actually help some of you too is how I would approach it as well is that you can kind of do things a couple of different ways, but many of you are going to want to like write the operator output operator, because it's when we write code, it's really nice to print stuff out, isn't it? Just like run code and print stuff out. If you were being cheeky, you could obviously write the output iterator by getting an iterator to yourself begin and .end, and then like iterate through it and print out this string and stuff and do all that. But I do think because iterators for many of you might feel like a harder part of it, the best thing you can do is actually just like write this out like manually. When I say manually, I mean just like write it as if I just gave you a class tomorrow and I was like, print all the stuff in it, and you just like, print it out, you know, like for loops and for loops. Because what'll happen then is that you have a way to print stuff out and actually see if what you're doing is working, but then as you build up confidence, you can actually go and then do the iterator properly. And then once you do the iterator properly, you'll have at least done that part of the assignment as well. Cool. Oh, yeah.
Just about time complexity.
Yeah, there's no stress testing of code, but tutors will be asked to kind of manually glance at stuff. So anytime we kind of mention a time complexity, it's usually because we would like you to do it in a way that's like, you know, maybe think about it a little bit more. Like a good example here is like with log n time, we're kind of saying like implied that you should be using, because an STL algorithm does a vector search, I think only if it's sorted. Yeah. Well, I guess if you know it's sorted, you can, that's what I mean. So like an example like this, if you were to just have like an unsorted vector of nodes, then if you just called the STL find algorithm on it, it's going to be ON because it's got to just iterate through every element. But us kind of saying it's log n makes you think a little bit about it. I'd say one general hint for me would be that remember that the vector is, it's probably in your interest to keep the vector sorted. Because if you look at like insert node, there's no real complexity requirements there either. So like you just maintain the vector to be sorted. If you're storing it as a vector, for instance, maybe some people store it as like a, you know, you can store it as a map or unordered sets as well, right? Like if you store an unordered sets are trees and they have very fast lookups. I think ordered sets are trees, so they have really quick lookup because they just like go through the binary tree. Like again, it's very open-ended, but that stuff is only there just to make sure that it forces you to think a little bit deeper about C++ in a couple of spots. Yeah.
Because it's asking like way too often. But if you look at like the edges in 2.5.
Edges in 2.5.
Like a bit, scroll down to 2.5.
Yeah. Go to what? Sorry, give me a sec. I've just got a family message that's like, sorry, what was it? It was yeah.
That's like log n plus e.
Yeah.
Why would you ever do like a log n like at all? It seems like you could just do it early. Instead of like asking for adds.
Yeah, I mean, obviously, if you're just storing it by itself, then yeah, you could just do it in log e time, because you just iterate through the. Oh, sorry, it's source to destination. My bad, I misread that. I was thinking about it as like all edges. Yeah, so source to destination, start with the unweighted edge if it exists, and the rest of the weighted edges in ascending order. I remember having a conversation about log n plus e, but it was in relation to something else. I mean, these are usually worst case complexities. Some of you might do them quicker. So like, yeah, you can definitely do it quicker in log n plus, than log n plus e. I'm just trying to figure out if that's a typo or not, because I'm trying to figure out what the log n plus e one would be. Well, I guess you have to, I guess you have to search through all the nodes.
But that's like bounded by E. It's going to be more edges than the other ones. If it's connected graph, it's going to be more edges.
Yeah, they could be way more nodes than edges. So it probably, yeah, because I guess like you have to find the node first. Because like if you think about it, you pass in the node you want. You have to find that node, which might be log n time, and then like that node goes to maybe like 1,000 other nodes. So then it's like you've got all these 1,000 other nodes. Because you think about it at scale, it starts to get a bit easier. You've got 1,000 other nodes that this node goes to, so you got to like find all those like node edge pairs or some equivalent where it's like those two things match up. And then you got to loop through every possible edge that exists. Like edge makes sense because you're returning all the edges, right? So it's got to be E. But yeah, log n because you probably have to find the node. Because without it, like, I mean, but again, it depends on the structure. Because if you had some kind of, but I don't even know if a structure exists like that. Unless you had some kind of weirdo structure where it was like, you literally were like, I'm going to create a standard map of like standard pairs of node to like standard tuples of like, or like to an edge or something. You know, maybe something like that could get faster because you can instantly determine, you know, where the list of edges is. But I guess like a lot of implementations, I imagine, like, let me think about the example one, like a map of n. Yeah, because in this case, you still actually have to like, yeah, because the number of like pairs of nodes to edges you're going to have is going to be way bigger than E. It's going to be like E times n, I believe. Is it? No, not E times n. That doesn't make any sense. Anyway, the point is that like in this case, there's still an iterative step to like figure it out. Because if this was just a vector of edges, it would be really easy. But again, the structure kind of depends on it. What I would probably say that might be useful for you all is like, I would use the complexity like not just as a worst case, but also as like maybe a hint. Because the complexities originally come from, so Chris wrote the complexity parts of the assignment back in 2019. Chris also can over-engineer things sometimes, so maybe it's not the best way to approach it, but he's also very, very smart. So my point is, I would lean into the complexities as an indicator as to a suggested way to store stuff. Because if you're doing stuff that's faster, say you have one function you implement that's like way faster than complexity, then you're noticing this other function you're writing is like really hard to do, like just wildly difficult. Then maybe you're constraining yourself by the data structure. And if you just picked a different representation, you'd find both of them kind of like, you know, medium difficulty. Yeah.
For the edge function that we just mentioned, is it only about the direct edges between two nodes that are adjacent, or is it path mapping?
Yeah, I think it's just for one node. Yeah.
So it's just like
Yeah.
Yeah. So make the login edge.
Yeah.
I thought it was good.
Yeah. It's fun though. I kind of think assignment 2 is a little boring sometimes, if you know what I mean. Like, you don't really feel like you're solving anything unique. You know, like what's the most exciting thing you do? You print out a string that's missing a few characters. Like, whoop-de-doo. This one actually feels like a bit more problem solving, which is good. Please keep posting stuff on the forum for sure. Maybe don't post any of the 2 questions that we asked, because someone's already posted it, no doubt, and I'll talk to the tutors anyway, and we'll get that updated pretty quick. Keep an eye out for merge requests on the side here. Remember, we do push them out to your repo whenever they happen. Yeah. Anything else? Okay. Well, thank you all. Have a great evening. I'm sure I'll see you around somewhere on campus or in life, but otherwise I'll probably talk to you the next couple weeks, next week and a half online. Have a safe trip home.